I'll just speed it up a little bit. Then I'm going to talk about HTTP3 today for everyone. So I'm Daniel. I've been here before. This is my 11th talk at FOSDEM, actually. And it's, if anything, this sort of audience makes your pulse go up a little bit. But I started doing HTTP a long time ago. I had this little hobby project. Some of you might have known it. I started it, and I work with it daily since then. It's fun. You should try it. I work for Wolf SSL doing curl stuff every day. But today I'm going to talk about stuff done within the organization IETF, where I'm participating and working with a lot of other people. So this is what I'm about to try to squeeze in my 45 minutes or so. So we did HTTP 1, 2, and we're going to 3. There are some problems along the way. That's why 3 is coming, right? I'm going to explain a little bit about them. How quick is the solution to those problems, and a little bit about HTTP 3 on top of quick. Some of the challenges with running this tomorrow or now, and something about it when it's about to come, or maybe, I don't know. I talked about this last year. Yes, this is not exactly the same, I promise, but you might recognize a few things because HTTP 3 is still number 3. So this is how it started. This is a picture from the 90s. We started with HTTP 1, actually. It shipped in, well, HTTP 1.1, no, 1.0 actually shipped in 1996, and then it took a long time, and then we did HTTP 2, 2015, and now we're working on HTTP 3. So it's get a little bit faster. So HTTP is this protocol. You've all seen it, you've all played with it. It looks like that. A client asks for something from a server, request and a headers, and your server responds with sort of a code and the headers and the body and stuff. You've seen it. It's there. It's going to be like that in the future as well. So HTTP, we started out this journey over TCP. Well, we still do it over TCP. So TCP, networking 101, it's like a chain of links. Basically, IP packages connected. So sort of we send them over the wire. And establish a connection. There's a 3-way handshake. Ping, pong, ping, to get establish that connection. 3 ways, 3 times across the network. And we get that connection, and we can send data over with, in a reliable byte stream, sort of. And it's in clear text. So anyone reading or snooping on the network can see your traffic. TCP, the first RFC, 1981. Celebrating 40 years next year. Trusted, we know it, we've used it, it works, it's there. Yep. But we're talking HTTPS these days, right? So HTTP works over TCP, but we're not talking HTTP clear text, we're talking HTTPS. And do we? Yes, we do, because page loads done by Firefox on the internet today, well, this is divided by continents from Firefox data, so there's somewhere around 80%, maybe more, maybe up to 90% of all page loads, HTTPS. Basically, the web is going HTTPS. The same data from Chrome, split on platforms instead. Yeah, some of them upwards 90, some of them only 70. But that trend is rather clear. It's growing. The web and everything is going more and more encrypted. We're talking HTTPS. So it's not only HTTP, right? HTTP over TCP, but we're talking HTTPS here, so we're adding TLS to the mix. TLS is that transport layer security we add on top, or sort of, so that we get security. And with TLS, we usually also add another extra round trip to get that TLS connection. 1, actually, sometimes 4, back and forth. Anyway, it depends on version and stuff. So with this, we get privacy and security. Nobody can snoop on your traffic. Nobody can change your traffic. And you know you're actually sure that you're talking to the right server in the other end. Excellent. That's what we need. So this is what we have. We have IP. We do TCP over that. We have TLS to secure that. And we do HTTP over that. HTTPS. What we know and used and love and every day, everywhere. So back again, TCP is done over, HTTP is done over TCP. So we started out, actually, HTTP 1.1, the great improvement to HTTP 1.0 was shipped in 1997. It was a great improvement to 1.0 because we suddenly fixed how we use TCP connections. Now we could reuse TCP connections. We couldn't do that with HTTP 1.0. Yay. But over the years, people come up with, we want to have many images, many JavaScripts, many style sheets, hundreds of objects on every page. Wait a minute, we only have how many connections? Let's come up with new ways to do more connections in parallel. So all the browsers today do many connections in parallel, and you can trick it to do even more parallel connections. So we went to that world. So now we're into a world with a lot of parallel connections. So many that we have to kill them off really often because there are too many to keep up all the time. So the median number of HTTP requests done per TCP request in Firefox is 1. So basically, they're all created, used, shut down, created, used, shut down. And TCP is really inefficient in the beginning because it has a slow start period. So they never get up to speed. So within HTTP 1.1 world, we can never use TCP good enough to actually get fast transfers. That's just it. It doesn't work. And we also got this fine thing that we call HTTP head-of-line blocking, because we have a finite number of connections, typically 6 per host name by a browser. And your typical website has many more than 6 objects. It's 100 images and style sheets and stuff. So you have to use those 6 connections to download those hundreds of objects. But on which of those 6 connections will you put your next request for the next object? It's a really difficult problem. It's like, in the supermarket when you have those line to cashiers. Which one is the fastest? Not the one you pick, right? That's going to be the trainee or something. Nah, you never know, or an annoying customer ahead of you. The browsers and HTTP clients, they have this problem. And of course, the entire world and everyone in here too, have come up with fine and ingenious ways to work around these problems. Put everything in a single file, put all JavaScripts in a single blob, do whatever fun things, invent new host names so that the browser will do many more connections. So yeah, you can be creative. But to sort of combat all those funny workarounds and take a unified effort, we created HTTP2 and shipped that in 2015. So all those funny workarounds into the protocol instead. And now we're going into a world with a single connection per host. Not 48, 1. That's much better because now TCP can get up to speed. We can saturate the bandwidth in both directions much better. Congestion control, everything is fine and dandy. We have many parallel streams over that single connection, so we get much better parallelism. But instead, we fell into another trap. Oh, now we got TCP head-of-line blocking instead of the previous HTTP head-of-line blocking. So now typically, we can have 100 streams over that single TCP connection. And when we lose one little packet because we have a crappy network and we need to retransmit that single packet, 100 streams are waiting for that single packet to get retransmitted. And then it gets retransmitted, and 100 streams can continue again, and then we lose another packet. Everyone has to wait. Not ideal. And at the same time, a long-going trend in the internet is this thing we call ossification that's been going on in parallel with everything else. Ossification is this effect that, everything is full of boxes, or the internet is. Routers, gateways, load balancers, Wi-Fi routers, whatever. A lot of boxes out there. And they're all installed at some point in time in your networks. And they run software, and they all know how the network works at the time you install that box, or someone installed that box. They very rarely actually know how the future is going to be, and they're all afraid of the future. So they know sort of, if it was a 0 today, it will never be anything else but zeros. We know that. So, and we never upgrade these boxes. We buy them and put them in the networks. We upgrade our servers, we do, actually, some of us do, every year or so. And the browsers, they upgrade themselves basically every week, sort of automatically. So the edges, they upgrade. The middle, it's stuck in time. And they know how the network worked when we got those boxes and installed them 5 years ago, 10 years ago. I'll just to really drive this in. So that's me, and there's the website. And all of those little machines in there, they're middle boxes somewhere. They're stuck in time. And their mission is to drive the network as the network worked when we installed them. Today, yesterday, a few years ago. This has a fun effect. Ossification, we call it. And some things like, wait a minute, you can do HTTP2 in clear text? Right, you just upgrade HTTP2. You don't have to do that over HTTPS. In theory, right? Because a lot of these boxes, they know that if you speak TCP port 80, that means HTTP 1.1. So whatever you speak on TCP port 80, those boxes will help you speak HTTP 1.1. So if you speak something else, they will just ruin your traffic completely. This to the extent that no browser today uses it. One browser in particular specifically intended to, yes, we were going to support it. until they tried. So they figured out that a lot of boxes help you. So no, you have to hide your traffic in encryption to make sure that it actually works. And wait a minute, we can improve TCP instead of doing it. Why not invent a way to send data earlier in the TCP handshake? We can call it TFO, TCP Fast Open. It's an invention from 10 years ago, so excellent. So if you talk to a server before, you can send data already in the first packet in the TCP handshake, that three-way handshake. Much faster, you can gain a lot of latency there. Let's do that. It took 5-7 years until all kernels of the three big platforms supported it. Yay, now we can do it on Windows, on Mac, and Linux. The browsers started to try it. Does it work? No. Those boxes, they know how a TCP header is supposed to look like. So if you set those little extra bits in the TCP headers that says, try TCP Fast Open, a number of them will just throw it away. So the TCP Fast Open turns out to be TCP Slow Open in quite a number of times. So now no operating system and no browser enables TFO by default because it doesn't really work across the web. And sort of this list goes on. If you want to try to introduce a new transport protocol, next to TCP and UDP across the internet, it doesn't work either because your Wi-Fi router at home, it can only NAT those two protocols and nothing else. So it'll just stop already there. So no, it won't be any new transport protocols either. So we can invent stuff over HTTP level instead. Brotli is a compression algorithm, much better than gzip for some purposes. Excellent. Wait a minute. A lot of those boxes, they know HTTP compression. That means gzip. So if you send compression, it'll help you. So X% of those connections will simply get ruined traffic because some boxes in between have fixed your traffic along the way. So of course, the browsers can do Brotli, but they only do Brotli now over HTTPS connections. So hide it from all those boxes. Encrypted is fine. So basically, this trend goes on. So this completely stops future innovation in a lot of these protocols. If you do it in the clear, someone along the way will ruin your day. And it's not going to be fun. It's not going to be fun. So we need to encrypt more encryption. Make everything a random noise to every box in between, and they don't know what it is. They can't ruin it. So that's the way we're going. So we need to improve them in spite of this ossification thing by simply making sure that they cannot see what you're doing. They cannot this is the way it's going to be forever just because we did it today. That's one of the things that sort of led to the creation of the Quick working group in the IETF. That's the official logo, and I just wanted to drive a special thing home. Quick is a name, not an acronym, whatever you think. It doesn't stand for anything, it's a name. Why is it all in uppercase? It's that we can shout it, I think. But it's a name. It doesn't stand for anything. So a lot of companies immediately took interest in this. All of these and more are sending people to this working group in the IETF. And it has been a fierce participation and activity since it started in 2016. So this is a new transport protocol, even though I said you can't do it on TCP UDP layer, but still. So this is built again on experiments and tests from Google. Pretty much they did it with HTTP2. You remember they did speeded, that became HTTP2 eventually from the IETF. Now they did their experiments, and to make everything more complicated this time, they call it Quick, and let me go back to that. So they deployed this already in 2013, so it's been going on for a while, and they have a fairly, you might not know this, but they have fairly well-used client and some popular services, and that makes them an excellent place to do these wide-scale experiments. Does it work really? 1 billion clients against our 1 billion servers. So yes, they proved that it actually works, and it improves a lot of things. So they took that to the IETF in 2015. Let's make this a standard instead of us making funny things in our corner. So yes, the IETF agreed with a bunch of caveats and conditions, and it created the working group for Quick in 2016. Two of the conditions, well, I could basically possibly add this first, say that my first line here, Google created Quick, their version of Quick, basically sending HTTP2 frames over UDP and sort of demuxing it in the other end and inserting it in your HTTP2 stack. Sort of just translate it, send it over UDP, translate it back as HTTP2. And in the IETF, they said, well, that is a really weird sort of layer violation. Why would you do that all in just one mushy layer? Let's split it up. Let's make it a transport protocol and an application layer protocol. So we do quick, and we do an application layer on top of that. And we need to have proper encryption and not your homegrown thing. We're going with TLS. So when you do a new transport, you can do a lot of things. You can fix this head-of-line blocking problem. I'll get back to how that works. And why not fix that TFO thing I mentioned, send data earlier in the handshake? Now I have a sort of a new chance to fix all those problems we've had in transport since that first RFC 1981. A lot of transport people, they have sort of a piped up list of fun things to do in transport. Woohoo, the chance to redo it. So a lot of fun things are coming in. And for example, why tie a connection to your IP, right? We did that back in the 80s, and I don't think anyone really expected the explosion of IP addresses per host. So, you know, when you're walking out from your Wi-Fi to your cellular network, you have two different interfaces in your system, and you have different IP addresses. What happens with your connection? In a TCP connection world, that's tied to your IP address, which is tied to your network interface. You have to open a new connection, not with Quick, but it's because it's not tied to your IP. It can transition between the network interfaces because it's tied to your connection ID. And more encryption, always encryption. There's no clear text version of Quick. It's even more encrypted than TCP with TLS because it's fewer parts of the header in the clear. So basically a few clear text packets in the beginning in the handshake, then everything else encrypted. Just encrypted, basically noise to everyone in between. So this is hopefully going to make it ensure that we can do future development. Hopefully this means that we can make a quick version 2 in the future without a load of those boxes knowing and drawing conclusions from the traffic patterns, because there shouldn't be much of a traffic pattern. So we build this on top of UDP. We pretend basically that UDP is the IP. So we move everything up one layer. We do everything over UDP. We write a reliable transport protocol in user space, and we're sending everything over UDP. It's a little bit like reinventing TCP and TLS in one layer and do it over UDP. And no, it's not UDP. We're using UDP. It is not UDP. So UDP, you send whatever you want. It might end up in the other end. It could actually change order. There's no resend. There's no flow control. But we're not doing that. We're using UDP, so we have to add all of those stuff on top of UDP. So we add connections and reliability and flow control, and we have streams, and we have security and stuff on top of UDP. So Quick is a new transport protocol. TCP is out, Quick is in. So Quick also then provides streams, for example. So what we had before in, for example, HTTP2, we have it in other protocols too, like SSH or SCTP. We have individual logical streams within the connection. So we can actually send many logical flows with a single connection. And you can actually store them from both ends, and you can actually make them bidirectional or unidirectional. So a little bit more complicated than before. And possibly the biggest point with these streams is that they're independent. What does that mean? Why they're independent? That means that if we send them, we know what's in each packet when we send Quick. If we lose a packet along the way, we know which streams those packets affect. So if we have 100 streams again, we lose a packet, we know which streams are in that lost packet. The other streams can go on. So maybe there were 2 streams affected by that packet. Then the other 98 streams can go on and continue. And just those 2 streams waiting for that lost packet have to wait, retransmit that lost packet, and those 2 streams can go on. They're independent, but internally they're all reliable and in order and everything. So just to sort of illustrate that with some fun image that I could draw. So TCP, I like to illustrate, again, like a chain with individual links. And here, if you're sending 2 streams, the green stream and the red stream, if you lose one of those, the green one, the red one also has to wait, right? Because it's one single link. If one link is gone, we have to wait until that link is repaired. But in Quick, the streams are independent. It doesn't matter. If we lose a yellow one, the blue one can go on anyway. They're independent. So that's a transport protocol, Quick. So when we provide a transport protocol called Quick. We put an application layer on top of that, right? And the application layer gets streams for free because it's in the transport layer. So it could then virtually be any protocol. And when Google first brought this to the IETF, the first discussion was like, yeah, we should make sure that it works with more than one protocol, not only for HTTP. We should start with DNS and HTTP. Great, but a little time-consuming, so we'll just postpone the DNS part, focus on the HTTP one. But it doesn't matter, but the intention is there and the separation exists. So it is actually an application layer on top of a transport layer. So there will definitely be more protocols on top of Quick once Quick ships, because there's a sort of a piped-up demand. A lot of people are just waiting for Quick to ship to make sure that they can make their protocols translated over to Quick instead of TCP. So that's Quick. That's a transport protocol. So when we talk about HTTP 3, that's how we make HTTP over this new transport protocol. HTTP is the same as always, right? That's me, and that's the server, and we send the request, and there's a method and path, headers, maybe a body, and we get a response and headers and a body. I showed you in the beginning. That's HTTP, and it's still going to be that. Most people are not going to care about how it's being transferred over the wire. Doesn't matter. This is HTTP for us. HTTP is the same but different. We started out with a protocol in ASCII. We translated it to HTTP2. We did everything binary, and we did all the multiplexing in the HTTP layer. And now we took away the multiplexing and put it in the Quick layer instead. But we're still basically HTTP2-like done over Quick. So just back again to how this sort of translates to network stack view. This is the IP, and this is the old one, right? HTTP1, HTTP2, pretty much the same. Right, HTTP2 actually says that you have to use TLS 1.2, but anyway, it's the TLS layer. So, but instead now, we're building on UDP, and we put this huge Quick blob there, TLS 1.3, and we add HTTP 3 on that, and the streams have sort of moved down one layer. A lot of new stuff, right? At least in sort of, there's a lot of things to make Quick work, but HTTP 3 is not that different than HTTP 2. So if you just look at sort of a basic feature comparison, yeah, we have a different transport, we have streams, we can do clear text. We cannot do clear text versions anymore, but in practice, we don't do that with HTTP 2 anyway because of what the browsers do. The streams are independent, but that's sort of a minor difference. We're going to do header compression, and we're going to do server push, and possibly better early data. But they're all sort of, yeah, we're doing the HTTP 2-like features, but it's now HTTP 3 because it's over Quick. And we're changing the prioritization thing over HTTP 3. It's actually completely gone right now in HTTP 3. It is messy in HTTP 2. And in 35 minutes, you can hear a talk by Robin Marks about it. It's a fun subject. But no, you're not going to fit in the room anyway. So is this going to be faster, better, cooler, whatever? I think it's going to be faster thanks to Quick, because Quick is going to make your handshakes much faster. Early numbers from Google from years ago when they tried their version show that upwards around 70% of the connections they saw were able to establish in a zero RTT way. Basically no handshake at all because you'd had the connection with it before. And zero RTT is much fewer RTTs like than 5 or 7 what you get with TLS and TCP. And you get early data that actually works, so you should be able to send a lot more data much earlier in the handshake. So yes, it should be a really good latency improvement for those first important packets, especially in HTTP and such protocols. And the independent streams are really going to be good, especially for you with crappy networks, which typically aren't us in the Western world. But the worse network you have, the better Quick and HTTP 3 is going to get, I think, in comparison to previous protocols. And by how much, I won't show you any numbers because we're still in early days. It hasn't been shipped. The protocol isn't done. There is no done code, so nobody is actually willing to stick out their necks and say exactly how much faster it'll be or not, so it remains to be seen. Numbers from Google Quick Days showed that it can be better, from a little better to much better, depending on your use case and what you're doing. Okay, so how do you get to this world of HTTP 3 over quick that is done over UDP when HTTPS:// means TCP, right? So if you ever try to check the internet, you've seen these URLs in a few places that they're not really possible to replace, right? We can't change these to anything else. We have these HTTPS:// URLs, we have to work with them, and they actually imply that you connect to TCP port 443 with a TLS establishment afterwards or on top. So how do you get to HTTP 3 from that? Easy. You use this fun header. This service over there. So you have an old service header. So you actually have to connect to the server with the old style, legacy HTTP 2 or HTTP 1 first. And talk to it, and you get a server back that says, hey, I'm also available over there for this period of time, and I speak this protocol over there. So that's how you're supposed to do this per the spec. So of course, your browser won't it'll do this in the background, of course, and try. If it can do this, it can upgrade and use HTTP 3 the next time you go to that server. But you also end up in this fun situation that UDP, wide-scale, really high-speed internet data, that's something new. Most organizations and companies, they have basically blocked UDP already because that's mostly done for DDoS attacks and stuff. So block it or throttle it. So when you do that, my server is over there, and your client tries to connect to it, many times it won't work because your organization or your company have blocked UDP. So when you shut down your laptop and bring it home again, it'll work because at home you won't block UDP. But okay, so I'm sure that browsers and other users, they're going to raise these connections. Why not just try both, right? Try the old connection and the new connection at the same time. And as I said, it's going to be needed anyway, because when you shut down your laptop and you bring it home and you open it up again, maybe HTTP 3 works now, maybe it doesn't, because someone is going to block it in one of the situations and not in the other. So there's going to be a lot of probing, stress testing, raising them against each other. And quick connections are verifying the server certificate anyway, right? So even if you just make a bet, it might be a quick server there. And if it connects, you know, because you validate the server certificate. So you know that you actually connect to the correct one anyway. And there's also another effort in DNS. It's called, quite a mouthful, HTTPS SVC, which is basically the old service header put into DNS. So you're supposed to look up in the DNS first if you'll be able to connect to the server, or which server to connect to when you want to speak HTTP 3. So that's how you're supposed to do it. So, okay, assuming this all lands, and how will we do this? Will it work? Will HTTP 3 be the best thing ever, starting immediately? So there are a few challenges. First, there are some things. We do this over UDP. I mentioned a lot of organizations and companies block connections. So somewhere around 3, 7, 20% of connections from clients to servers will just fail because someone along the way has blocked UDP, because UDP is bad and it's mostly DDoS. Anyway, DDoS and DNS. So all clients then need to have fallback algorithms, and they have to work transparently because that's what your users want to use, right? And this also have this, of course, the reverse incentive that since everyone is going to fall back anyway, it's pretty easy to block UDP because most clients will just silently fall back anyway, so it's going to be interesting. And right, it's a challenge for the deployment side. If you you deploy your servers, but the traffic, it looks like a DDoS attack. So you need to handle that in new ways that you didn't do before. Actually, I think the deployment of the service is going to be possibly the most challenging things, because you're not going to run things, your load servers, load balancers, and everything is going to be new things. And so, okay, it only takes about 3 times the CPU as before to sort of serve the same bandwidth as you did with HTTP 2. And that's quite a big investment. Maybe that's we'll make you hold it off for a little while. But I mean, it's still early days. And why does it do this? How can anyone accept this? But first, it has this amusing situation that UDP is really unoptimized in Linux, and you would imagine that UDP is really dead simple. Why would that be more inefficient than TCP? But we've actually been polishing TCP for decades, right? Because we've used that for high-speed transfers. UDP, not so much. So there's a lot of things to work on to make sure that UDP is faster in the kernels. And for example, we have really crappy APIs for UDP from user space. So they're really not made for high-volume UDP speed transfers. That is also being worked on. And of course, there's no hardware offload for Quick. And anyone who knows a little bit about serving TLS in a big server farm, you have hardware offload to take care of the crypto stuff in TLS. That's not there for Quick yet because TLS is different in Quick. I'll get back to that about now. So when Google took their version of Quick, which then confusingly, it's also called Quick. We call it Google Quick to sort of, but Quick became Quick in the IETF, and they had their own crypto when they brought it to IETF, and IETF said, we can have it like that, we need to have TLS 1.3. This was actually slightly before it became an RFC and everything, but sure, we now have TLS 1.3, but TLS is made to be done over TCP. And now, to just be a little bit technical here, but we send records of TLS over TCP, basically. And over Quick, we send messages, because TLS records contains messages. Basically, it looks like this. I'll just show you a little image. So this is how you do it over TCP. So you have to send frames like this with messages inside. But that seemed completely pointless. Why would you have those frames? You don't need them when you do it in Quick, because Quick is a new protocol, so we can just send the messages. Fine, that's sort of, get rid of the crap we don't need, just send the messages. Well, apart from the little detail that no TLS stacks have APIs for this. So, yeah, we just have to fix all TLS libraries, right? Easy peasy. So, and that they also need a few other crypto secrets exposed from the TLS layer to the Quick stack. So, we just need all TLS libraries to be fixed first, too. Sure. I'll get back to that as well. So, and sure, you're right. All these implementations are in userland, right? Which is probably not always a bad thing because it makes it really easy to iterate and try out, right? So when Google tested it out, experiment, it was really easy to iterate. They could sort of bump their versions every other day, upgrade the browser, upgrade the server, and just try it. It worked fine, and it sort of, but it also makes you as an application author, you have to get married to one of these libraries and hope that it'll stick around for a while. And there's no standard API, so of course you get married even closer to one of these. And you have this kernel user space transition all the time. So back again to the APIs, to the kernel. So how many back and forth, how much time do you actually waste by going back and forth kernel space, user space? So then your obvious question is, will this then be moved into the kernel? Because, I mean, that's where we're used to. TCP is there, right? And we're used to having the transport protocols and stuff in kernels. And I don't have the answer for this. Oh, maybe it will. I don't think it'll happen soon. I know there are some efforts to do it, but there are also some new fun interactions between Quick and Quick and HTTP3, which should be in the kernel and how. And would anyone writing a kernel really want a new sort of TLS implementation in the kernel? I don't know. I have my doubts that it'll be a fast development. So I don't think so in near time. So what about tooling? There's a lack of tooling, of course. So this is a totally new area, right? We're throwing out TCP. We've used TCP for quite a while, right? TCP dump. Who hasn't used that, right? No, not anymore, right? All those concepts about segment numbers and windowing and stuff, no, that's gone. So now we need new tools. And okay, Wireshark is there, of course. You get it the latest, and you can actually use that today, and it's excellent. And there are tools coming like qlog, qvis. Qlog is a sort of a standardized logging for Quick service and implementations in general, actually. And qvis is a visualizer of those logs. So there are tools coming, but there's definitely a shortage because this is really new stuff. So a little bit thin there. A lot of work to do. So, okay, when will this ship? And This is actually, so the Quick Working Group has a charter when it says we have some milestones for when we will ship, and it says there it's going to ship in July 2019. I'm only slightly disingenuous because they actually argue, there's a change suggested that will actually be applied, I think, in the coming week, and then they will remove the year completely, and there's no milestone anymore. But I would say that maybe it'll be around July 2020, perhaps. I've talked about HTTP 3 many times, and this is one of these slides I tend to change the most, sort of postpone it, or maybe this time, maybe not, I don't know. It's really hard to tell. There's a lot of strong wills in the working group, and they want to do it right rather than soon. So who knows? Maybe 2021. So there are a lot of HTTP 3 and quick implementations. I'd say over a dozen here, but I think there are even more. So all those companies I showed you before, they all have their own stacks. So there's a multitude of them. You can get them in many languages. There's nothing that prevents you from jumping in immediately and start fiddling with them. There are monthly interrupts, which actually proves then that the specifications actually work. Most of these implementations can actually interrupt with each other to a fairly high degree at least. And we're on draft number 25 right now. So what's good? Curl supports it. That's good, right? And if you really insist, you can also use one of the browsers. Or if you use one of those Canary ones or Firefox Nightly, you can enable it. I'll show you in a second. You can also enable it in those servers. And there's an Nginx patch that runs with Quiche, which is a quick library, so that you can run your own experiments already today. They're also up to date with the latest draft version. And I mentioned already Wireshark can analyze these streams. But not everyone is on track yet. There's no Safari version, and there's no word from these, the big standard open source servers. I don't know when they're going to do it. I don't think there are any official news from any of them. And then there's this fun thing. I'm back again to the TLS situation. We only have to change all the TLS libraries. How hard can that be? Well, that's the pull request for OpenSSL to make the necessary change for the API. 87, 97, it's still being discussed, so it hasn't even been merged. So it'll take a while, I think. And then that's about getting merged into OpenSSL Git master until that gets shipped in a release and then deployed in your Linux servers. I think it'll take a while. So how do you want to run this immediately today? Then you just fire up one of these Canary versions of the browsers, and you enter that fun command line option. And if you're a little bit slow and just wait a few more days, I think you can change the 24 to a 25, because then they're going to upgrade to 25. And if you want to do it with Firefox, you just find that little thing in the about config, and you enable it. Easy. And you can find test servers, even if there are basically no one. You can actually go to Facebook. And Cloudflare runs some public ones. Other ones, they are just a few test servers. Early days still. You can do it with curl. And I support the latest draft version. You can do that server over there version approach. And I support 2 different backends, so you can pick whichever library you want to use of these 2, and GTCP2 and Quiche. And the fallback is tricky, so we don't do that in curl yet. I don't know really how to handle that. I'll figure it out. So you can try it. It's fun. And if you would do that, it would look like this. So you just ask for HTTP 3 instead of anything else, and it'll just show exactly like HTTP looks like. There's no difference, really. So just to show you some of the problems that we have to ship this. So you want to ship HTTP 3 enabled curl. When, right? First, we have some specifications. They haven't landed. Mid-2020, maybe. And then we have these libraries that we are using to do all of this binary stuff. They're all in alpha versions, right? Because the draft versions keep changing. So they're probably going to ship after the specifications. And then I'm just going to have a few deployed servers before we can do this, right? Only Facebook and 2 Cloudflare servers are probably not enough. Browser support would be good. They're actually pretty crappy still. And so then I want to fix libcurl, and then we just have to have those TLS library situation fixed. How hard can it be to ship a TLS library API? And then we can ship curl. It might not be tomorrow. So I'm looking into this crystal ball, how will this look in the future? So yeah, this will take time. I mentioned quite a few obstacles along the way here. So yes, it'll take some time, and I think it will grow a little bit slower than HTTP2 did, and then I would say that HTTP2 didn't grow really fast. But Quick is also here for the long term, so I think Quick is truly the TCP replacement, the only existing and sort of viable replacement for TCP that has been done for a very long time. And there's a big effort here and a lot of big muscles and big companies behind this. So I'm pretty certain that Quick will become the TCP replacement. Maybe not tomorrow, maybe not 2021, but it's going to be there down the line. And the future then, once this is shipped, people are waiting to add more stuff, multipath, forward error correction, unreliable streams. So you can mix reliable and unreliable streams within the same connection, right? Bring UDP back into Quick. Or what about partial reliability? Only a little bit. It's actually sort of pushed for by video people. Of course, more application protocols. So there's a huge demand of people waiting. Once this ships, there's going to be more work. There's going to be more work on Quick version 2 as soon as Quick version 1 ships. So there's a lot of people waiting to do things. And always when I say this, a lot of you are still waiting for me to mention something about WebSockets, right? Sorry. That's not actually a part of HTTP at all, HTTP 3. Definitely not, so it's more of a thing on top. And this time we don't fix it either. You could, in theory, fix WebSockets exactly as people did for HTTP2, if you wanted to. But that's probably not how it's going to happen. It's going to happen in a completely different way, which is a new API and things for doing TCP-like things in JavaScript over the web protocols, called web transport. That's a draft for that. Right. Whew. Now you can wake up over there. HTTP 3 is coming. It's going to be encrypted all the time, over Quick, over UDP. There are a lot of challenges to do this, especially then in the server side, and might come mid-2020. I'm always the optimist. When I talked about HTTP 3 last year here at FOSDEM, I think I said mid-2019. Next year, I'm going to... I wrote a book about it, or a document at least. It's there. It's free. And I just wanted to say that since the acoustics in here is completely crappy and everyone is going to walk out the second I show you the next slide, I'm afraid the better way to ask me questions about this is out here or in the cafeteria in 5 minutes. But you can ask me questions now, too. Thank you.